Hello, my name is Brian Malyszka, and this is the element distinctness presentation. So, the element distinctness problem is the problem of telling if all elements of a list are distinct. So, as an example, in this first list, we have a list of 6 elements and none of them are equal, which means that it is distinct. However, in the second list, the first and last element are equal to 1, which means those two are not distinct, which means it returns no. So the point of this presentation is to prove the lower bound of this problem. And the lower bound is n log n. And in this proof, we will not be able to use the sorting proof in the element distinctness proof. So this is because in sorting, we rely on the total number of leaves on the decision tree, which the leaves in sorting is the total number of possible answers, which equals n factorial, and n factorial leads down to the lower bound of n log n. However, in element distinctness, we cannot rely on the total number of possible answers, as the total number of possible answers includes yes and no, which these two answers lead to a really silly n factorial. So, to begin this proof, we will need to visualize an n-dimensional space that is comparing values in the given list. In any dimension, there will be a distinct line that shows the possible no answers, while everywhere outside that line will return yes. So on this picture on the side, you can see that I've decided to set n equal to 2, just for ease. And you can see the red line here, and this red line gives all the all the no answers in the element distinctness problem, where, as you can see, 0.1 is equal to 0.1, and those two are not distinct because they're equal. So in claim 1, we will be using convexity, and convexity is the idea of an object such that 2 points on any part of that object will have a straight line connecting the 2 points. So on this cube, you can see the 2 points here, and there's a straight line going between those 2 points, and that straight line does not leave the object, and thus the object is convex. However, on this donut, you can see the 2 points, and the straight line goes right out of the donut, which means this is not convex. And actually, for the first claim of this proof, we really want to prove that R of L is connected. But convexity is equivalent to connectivity, and it's actually easier to work with, so we'll be using convexity. Alright, so our first claim is that R of L is connected, and R of L is defined as times that a leaf of the decision tree is able to be reached. So, we can define x and y to be 2 points in this space R of L. Suppose these 2 points both reach the same leaf L, then we can define a third point, z, such that this equation is true. And that means that z will be able to rest anywhere on the line between x and y. So, suppose x takes the less than branch, which means that x will be down in this lower half of the square. Then y must also take that branch to be able to reach L, the same leaf, as x. So by our definition of z up here, we can conclude that z will also be taking the same path to reach L, so that it follows the line to x between x and y. And since that straight line will reach L, it leads to R of L being convex, which means that R of L is connected. So we can use claim 1 and claim 2, which is if x is a list of distinct elements and y is a permutation of x, then x and y must reach separate yes leaves. And to prove that, we'll be using contradiction, and by way of contradiction, we can let x and y reach the same leaf defined as L. Because of claim 1, the path from x to y must pass through L. Because claim 1 is the R of L being connected, x and y, the path must be connected. We can define a third variable, z, on this path P, such that there is an indistinct element in z, and this is for the contradiction. And this is the proof of the indistinct element. So, there exists a pair of xy such that x1 is less than x2, while y1 is less or greater than y2. And since it's just permutations, we can say, just for an example, say this is 1 and this is 2. So then, since it's a different permutation, this will be 2 and this will be 1. And it's just a very simple permutation. Then we can rearrange this so that this is true. And since this is true, this can be defined as the lower half of that no line that we defined earlier here. So x1 minus x2 will be down here, and y1 minus y2 will be up here. Then, because those pairs must cross from the lower half to the upper half, there must be a point where the path crosses through distinct line. So, since it's up here and down here, there must be a line going from here to here that crosses straight through this no. And since z is on that path, z1 can be equal to z2. And since those two are equal, that means that there's an indistinct element in z, which contradicts our claim number 1, or I guess claim number 2, or it contradicts our claim 1, proving claim 2 to be true. Sorry. So the closing arguments. Because there are distinct yes leaves for each permutation of a set of numbers, we can thus use the same idea from the sorting lower bound proof. I know, I kind of contradicted myself. But since there are distinct yes leaves, that means there are n factorial permutations of a set of numbers, thus n leaves, and then our lower bound is n log n. Thank you very much, and this has been a lower bound proof for element distinctness.